Okay, we're going to take up one of the homework problems that I assigned from the calorimetry activity found in your activity manual. So the problem that I assigned for homework is found right here, question 5. And basically we're adding some 50 grams of lead, 70 grams of copper, 62 grams of aluminum, 125 grams of iron, into a calorimeter that contains 0.12 liters of water. Now each of these substances is at a different temperature, and what happens is eventually the system comes to an equilibrium temperature, and that's what we're asked to find out, the equilibrium temperature. So I've already started some of this, and basically I've written down everything that we know. So I have the temperature, the mass, and the specific heat for each of the substances. That the first row there is for lead, second row is for copper, third row is for aluminum, the fourth row is for iron, and finally the last row there is for water. Now one thing to note, you actually have to figure out the mass of the water. And it turns out the mass is just 0.12 kilograms, and I get that from the density, that's this first term right here, and the volume, and I had to convert that 0.12 liters into meters cubed. So you end up with 0.12 kilograms. Okay? So, what do we know? Well, we have to look at the heat exchanged with each substance. So let's first consider the heat exchanged with lead. So that is just equal to the mass of lead times the specific heat for lead times the change in temperature. So the change in temperature is going to be the equilibrium temperature minus the initial temperature of lead. Okay. We could do the same thing for copper. So maybe I should make that a subscript. So the heat exchanged with the copper is the mass of copper times the specific heat times T equilibrium minus the initial temperature of copper. We have also for aluminum, we get the mass of the aluminum times the specific heat of the aluminum times the difference between the equilibrium temperature and the initial temperature of aluminum. We do the same for iron, Mi times the specific heat of iron times the change in temperature of the iron. And finally we have the heat exchanged with the water, which is the mass of the water times the specific heat of water times T equilibrium minus the initial temperature of water. Okay, so far I really haven't done much. I've converted all the temperatures into Kelvin, I've written down all the temperatures, masses, specific heats, and I have the nice equation for the heat exchange with a substance given its mass and the temperature difference. So, all this stuff is right from your notes or right from the textbook. We haven't done any algebra or anything. So how are we going to find T equilibrium? Well, since this is an isolated system, the sum of all these Q's should equal 0. We shouldn't have any net change in the thermal heat of the calorimeter. So we have that QL plus Q C plus QA plus QI plus QW equals 0. Alright, now I'm going to solve this in a couple of steps, and you're going to have to verify each step. So all I have to do is plug in each of my Q's into this equation here. And once I do that and rearrange, I'll find that I'll get an equation that looks something like this. T equilibrium times ML alpha L plus MC alpha C plus MA alpha A plus Mi alpha I plus M water alpha water plus minus following M L alpha L T I L plus M C alpha C T I C plus M A, I'm going to run out of room, alpha A T I, that's a T, let me write that a little bit neater here, T I A plus, I don't want to cram it in, plus M, where was I, M I alpha I T I A plus M water alpha water T I water, and all of this is equal to 0. Sorry, that looks like a bit of a mess there. Hopefully it all makes sense. Make sure you follow the brackets. Anyways, there's two terms here. There's this term, T equilibrium times this bracket, then we subtract the everything else. Okay? Alright, so oops, sorry, I needed another page there. Oh, maybe I didn't. Okay, so what do we do next? Well, we want to solve for T equilibrium. So T equilibrium is just the following. It's, where are we? M L alpha L T I L plus M C alpha C T I C plus M A alpha A T I A plus, I'm going to run out of room again, M I alpha I T I I plus M water alpha water T I water. This is a bit of a mess, I'm sorry, and this is all divided by the following, M L alpha L plus M C alpha C plus M A alpha A plus M I alpha I plus M W alpha W. Okay, so we have a nice equation here for T equilibrium. Sorry, it's a bit of a mess here. Hopefully all the subscripts and superscripts make sense, as well as the brackets. So all that's left is to plug in all the values we have up here. So I'm not going to write them all out. I'm going to assume you guys are capable of doing that. And when you do this, you should end up with a T equilibrium of about 283 Kelvin, which is the same as 10 degrees Celsius. So at the end of the day, when all these things are added together, the equilibrium temperature of the system will be 10 degrees Celsius. Okay, I hope this video helps, and I will also try to post answers for questions 1 through 4 on my courses. So take a look for that in the future. Okay, thank you very much.